This morning we are going to look at the concept of operational amplifiers and also the concept of impedance. So the first thing that we're going to do is the concept of impedance, because that will help us to what comes later. So on the screen you have the example of three elements, basic elements of circuits, and we are going to look at this concept of impedance first. So let's start with the basic elements and the basic equations. So we have in here the first one. In this case, how do we write the constitutive equation of this? We say that the voltage across the resistor here is equal to the R times the current, yeah? And if you apply the Laplace transform to this, you can say that voltage of R in this domain is R times I of S, right? So in this case, we could write for the second one, V sub C is 1 over C, the integral of I dt, right? That's the basic equation. If we apply the Laplace transform for this, you will have voltage of C is 1 over C times S times I of S, right? Because the integration is always 1 over S. That's the reason for this. If you look at the voltage across the inductor, then you would say that this is L times di dt over here. And then we can write that the voltage across the inductor in this case is S times I of S. Take a look in here. This is the, you could say, let's write it here in the time domain. And this is in the S domain, or the Laplace domain, you could say. That's the, okay. But isn't it true that if we can write this in the what we are going to call it the impedance form, this resistance is like we are going to use a new letter. Let's call it Z for impedance, Z of R. So this is like having voltage of the resistor in the S domain is Z of R times I of S. So ZR is really R in this case. If we look at this as a, like I say, as if this would be a resistor, this Z of C, because you have the equation in here, you see, let's use a different color to illustrate that. This, in reality, this is our Z, see? Like that. But in here, this thing here is our Z. So we can write the equation that you have on the right hand side. You can write it that V sub C is equal to ZC times I of S, where ZC becomes 1 over CS. Okay, and if we do the same thing for this other one, like I said, this is the impedance of this L element, so you have that V of L of S, of course, is equal to L here, L times S excuse me, we're writing in the impedance form, so we have to put the Z, right? We have to put the Z of L times I of S. So you see all these forms, all these forms, this one, the bottom one, this thing here, and that they have the same format. So Z of the L then becomes L times S, and the impedance or the resistance form then it becomes this. See, so this is your, just to drive the point across, this Z of C is 1 over CS, like this, and then the impedance of L is S times L. See, so if this is true, then we can actually build a circuit and use these equivalences. So let's see, because we are let's see, so let me just do an example that will show you in your screen, just in an elementary way, circuit, a simple circuit with all these elements, and I'm going to show you how you will obtain the transfer function under those circumstances. So in here, let's just build this circuit in here. We're going to put the capacitor over here, and then we'll put the inductor over here like this, where this is the voltage here, this is the R element, this is C, and this of course is L. We know that this is the current I. So let's set up our objective. Okay, our objective is going to be to find the transfer function that relates the voltage C to the voltage in here. This is what we want. Remember, always the transfer function is an output in relationship to one input. This is something that you really need to have it clear in your mind, that a transfer function is always a relationship between an output and an input. What have we done in the past? In the past, we went ahead and wrote the equations of motion in the time domain. We apply the Laplace transform, and then we did the transfer function. This concept of impedance that I just show you on the right, you can actually use a symbol, a little symbol, different symbol, to indicate that you are working with impedances. So let me redraw the system here. I'm going to use this symbol here like this. Okay, and then I'm going to use this little symbol like this. They are not resistors because they are different elements, but they look like them. So if this is the case, I am going to put it in here as if this would be like ZR, then ZC, and then ZL. So it follows from this that if I write voltage in the S domain and I follow the equations here, you have that ZR times I of S plus ZC times I of S plus ZL times I of S, right? See? Any difficulty with that? The voltage here is going to be, in this case, Z for R is R. Yeah, I'll take the time. I'll do it again. So this is the Z for this is 1 over CS, right? Times I of S. And the other one is S times L times I of S. So from here you could say, look, voltage is equal to S times L plus 1 over CS plus R, just organizing it a little bit, okay, times I of S. And you can say, and the voltage across the capacitor that I have is 1 over CS times I of S, right? So if this is true, then it follows that I can find out what the transfer function is like this. If I go and put, okay, look, this is 1 over CS times I of S like this, and the other one was S times L plus 1 over CS plus R multiplied by I of S. Yeah? So what do we get here? This would cancel out, yeah? And I would get 1 over C times S multiplied by S times L plus 1 over C times S plus R yeah. So what will happen here? Let's keep going here. This is interesting because it's giving us already the transfer function form. So you have C times L times S squared plus you will have that C times R times S plus 1, right? Okay, so we concluding here based on these principles that we have applied that the transfer function here, we say transfer function of BC in relationship to B is equal to 1 over C times L times S squared plus C times R times S plus 1. And no matter what method I use, I should be able to obtain this transfer function. Now, if we go to, let's say we complicate the circuit and we advance to, let's say, a 2-loop circuit, the question is, using this concept how can we obtain the transfer function? So let's see if we do that. Let's just use our own, the same basic circuit, but we are going to add some elements to it. And here you had the capacitor, right? And then we have the inductor on the bottom in here. If you have a situation like this now, and then you put another resistor here, and you put a capacitor over here, let's say like that. Now what? You know for a fact that if you do this in the time domain and then you apply the Laplace domain to both differential equations on the loops, you will have to solve a system of two equations with two unknowns, right? That we do know. So how could we do it with this new method that I just told you about? In here we have, of course, I1, and then we have, of course, I sub 2 in here. And you see, this we'll call it R1. This we're going to call it R sub 2. This will be C sub 1. This will be C sub 2. And this would be L sub 1. And then, of course, we have voltage over here. Based on what I just told you, isn't it true that we could transform the system into an impedance equivalent circuit where you have this impedance here that is ZR1, and then you have this impedance here ZC1, and you have this impedance over here that would be ZL1, and then we'll have this impedance over here like this. You see, as if this would be transforming to a circuit as if they were resistors, you see. And this would be no, Z, and then ZC1, and then ZL1, and then B. You see, what I'm trying to tell you is that once you have produced these transformations, you can treat the system as if this would be a system of just resistors, and solve this in series or in parallel, So and you could do the state the two equations by doing the loops. It's okay. I mean, you could just say that B is equal to Z times R times I1 of S, and then you can say plus this Z of C sub 1 times I1 of S minus I sub 2, like that. And then you can say plus Z of L1 times I1 of S. And on the other one, you will have minus Z of L1 times I1 of S minus I sub 2 of S, and then plus Z of R sub 2 times I sub 2 of S, and then plus Z of C sub 2 times I sub 2 of S, like this. And then you are going to say from these equations in here, it's very obvious that you will have a system of equations very similar to what you had in the past. In other words, let's do it, because I would like to finish that. You put this is R, right, times I1 of S, and then you have plus this will be 1 over C times S times I1 minus I sub 2, and then you have plus S times L times I of S, like this, yeah, and then you have minus 1 over CS times I1 of S minus I2 of S, and this would hold for any number of loops. And then you have plus R sub Z of R sub 2, no, which would be R sub 2 times I sub 2 of S, and then plus 1 over C S times I sub 2. And isn't it true that from here you can write two equations, two unknowns in I1 and I2, and doing this you can find any transfer function in there. So that's how we do it using this concept of impedance.